conference. Yeah. Wow. I'm old, yes. Okay, so I'm going to be talking about dwarfs again. It's hard to move away from a topic so interesting. Oh, no, that's the wrong thing to do. 10 years and I'm still having technical difficulties. I got it. Yeah, I know exactly what to do. Now let's try to hit the right button. There we go. Okay, dwarf galaxies. And this time I'm going to focus primarily on the 10 to the 10 solar masses in dark matter. Now this is the type of galaxy we expect to form about 1 million solar masses in stars, and that makes it comparable to many of the local group dwarf galaxies, dwarf spheroidals, that we find in and around Milky Way and Andromeda. Another reason this is an important mass range is that we think this is the mass range where stellar feedback switches from being inefficient at lower masses to efficient at higher masses in forming dark matter cores. This is also the mass range where both in the central but also in the potential existence of any satellites, we expect these galaxies to be sensitive to the effects of reionization-induced feedback. Okay, so the simulation code I'm going to be talking about today, I think you all know some about, it's been talked about, but I'm just going to highlight a few of the differences because this is the second version of the code. We used a more accurate hydrodynamic solver. It's called MFM. It's a finite volume Lagrangian method, but it attempts to kind of bridge the gap between, although it's still primarily particle-based, it attempts to bridge the gap between grid and particle-based codes. We now are more conservative with a supernova ejecta. We do a solid angle weighting. It's also conserves linear momentum. Now the photoionization heating is slightly more accurate. It's a little bit, it's now allowed to propagate slightly out of its original computation zone, which means there's a little bit extra propagation. We got rid of this silly, unnecessary artificial pressure floor. We updated fitting functions for cooling tables, supernova yields, newer recombination rates, and code optimization. Now, the code optimization has allowed us to push to even higher and higher resolution. So, oh yeah, and so you can see, of course, these are some of the pictures of more massive galaxies formed with fire too. Very beautiful. Dwarfs don't look quite as interesting, but they're more interesting scientifically, I would argue. Okay, so I'm going to talk primarily about one of our dwarfs. M10Q has a quiescent merger history. It assembles most of its mass early. In our standard fire 2 resolution, or it's pretty high resolution, 250 solar masses, baryonic particle. It forms about just a little over 1 million solar masses. Now this is pretty high resolution. This is what I've been talking about the last couple years. But can we do better? Right, there's an arms race going on with resolution. And so this is just dark matter images. Now, since we already called this high res, I'm going to follow standard simulator or standard astronomy naming convention. We're just going to call this super duper high res. We pushed it higher. Now there's 250 million particles. The baryonic particle mass is only 30 solar masses, and as far as I'm pretty sure this is the highest resolution cosmological simulation ever run, super high force resolution as well. And it's so high that early this morning, very early, we got a little attention from someone at the very top. I was very impressed. I mean, he didn't quite get it exactly right. And he probably has other more important things that he should be paying attention to, but it's nice. It's nice to get some recognition. Okay, so what is the issue? When you start pushing to higher and higher resolution, though, you start to run into some problems that you maybe didn't run into with more massive particles. We use a Krupa IMF, and as you can see, it really cuts off at the high mass end here. So what we do in a traditional or a high-res simulation is we have one single star particle represent a single stellar population. However, once you start to get your particles below 100 solar masses, that becomes a little tricky because then you have each star particle maybe representing just a fraction of an O star. So instead, what we do is we stochastically sample the IMF. So every once in a great while, one of these particles represents a discrete integer number of massive stars. Now, that's also still not the correct way to do it. You should then hack off some gas particle nearby, but we're getting there. We're getting there. Okay, so of course, this is again just dark matter subhalo mass function, push to higher resolution, yeah, we're getting an order of magnitude more subhalos that are going down to an order of magnitude lower mass. Okay, so why do we want to simulate this mass range of dwarf at this high resolution? It's comparable to local group dwarf spheroidals. So just for something simple, like let's take the alpha to iron abundance. This is observed. These are M31 satellites, and you can see some of them have flat alpha to iron abundance, some are decreasing. This tells us about the time scale of star formation. It's going to be more flat if you had your star formation happen in a shorter time scale. And if you try to compare to just our standard high resolution, it's a little tricky to see what's going on. Maybe it's flat, maybe it goes down, there's a clump. Just look at how much nicer it is when we have 30 solar mass particle resolution. You can see a distinctive track, kind of what you'd expect. It goes up initially and then down. So this is just one example of the kind of things we can do with this sort of resolution. Okay, bursty star formation. There's a lot of talk about the burstiness of star formation, the blowout. This is the thing we expect, we think is responsible for creating dark matter cores, also inverting age gradients. We've heard a lot about that, but what we wanted to do was make sure that we're not artificially creating this burstiness. If you look at our Res 250, you can see it has these periods of absolutely no star formation. And this is when we think the gas has been blown out. But if you think about it, if you're dropping below about a solar mass every million years, and your star particle is 250 solar masses, it's going to take quite a long time to form a single star particle. Now, here you don't have, you have much smaller periods of this complete lack of star formation. Now, that's not the only way to measure burstiness. In fact, probably a better way is what fraction is formed in 10 megayears over 200 megayears, and that's actually pretty consistent between the resolution, but we wanted to, investigate this to see if these complete blowouts are, in some ways, a numerical artifact. That said, oh yeah, so why is that important? I already mentioned is because this is what we think is responsible for creating dark matter cores, especially this mass range. This is from T.K. Chan's paper showing that this range right here, exactly what I'm talking about, is right where we start to see possibly the beginning of core formation, not below and definitely above, and then it goes back down at higher masses. Okay, so this is just dark matter. Well, these are not dark matter only simulations, sorry. These are all hydro, but this is just the dark matter density profile. You can see that it's a little unclear in the high res whether it forms a core. In the super duper high res, it's much more pronounced. In addition, we can trust it down to lower radius because the power criterion means we can go much farther down in distance. Now, I was looking at this and I thought it was a little crazy because we're at about 10 to the minus 4 in ratio here. And it's, if we think of a core, but then I realized if you actually look at about where it's measuring, it's still consistent. So we're not off the chart. But I would say that we can say that, oh no, let's go back. We can say that we are forming cores, I would say, in 10 to the 10 solar mass halos. Okay, now on to whether these are their satellites or whether they exist or not. Farah already kind of mentioned it. Can tell us about what the effect reionization feedback has on the tiniest dark matter halos. What's the lowest mass galaxy that can form? So, harken back to 2 years ago, I talked about the Fire 1 version of this code. This is the exact same, this was dwarf too early from that. This is the same initial conditions, and we showed that dwarf too early formed a tiny satellite of a few times 10 to the 3 solar masses. It had an ancient stellar population, but now we have even higher resolution. We have a new version of the code. Let's see what happens here. Now I'm going to put the stars on. It's going to look a little messier because I'm just putting all the stars on the page or on the screen. Okay, well, that's a mess. I don't seem to really see anything. I ran a halo finder, and it told me there is a satellite there, 724 solar masses, but when I zoomed in, you can see actually there's nothing there. It needs to be investigated further, but it looks like this is sadly fake news. Okay, so what's different? Why is a satellite not forming in even the super duper high res version of this simulation with Fire 2? Okay, well, it could be a number of things. My plan is to go through these and try to figure out what it is. Solid angle weighting of supernova distribution. I'm not sure about that. We found that the greatest change in the centrals of more massive galaxies was actually due to the hydrosolver. I think something I've targeted is possibly since the photoionization, the local photoionization is now propagating a little further, that could have something to do with it. We've updated the fitting functions for cooling tables. My plan is to take a look at each one of these in turn and see if we can get that satellite to come back or not. Also trying currently, well, actually, yeah, lower star formation density threshold. And then finally, the last thing I'm going to talk about here is the reionization prescription. So I don't know if you all saw Jose and Yorbe's recent paper showing that pretty much all the reionization prescriptions we're using are wrong. Basically what happened is he went and looked at our standard Hart et al. Fauché-Giguère and showed that the actual ionization history predicted by those models is not what occurred in big box full radiative transfer simulations that they ran. What's actually happening is that we're reionizing the universe too early. And this was due to a blind extrapolation of the optical depth at high redshift. Now this has very important considerations for things such as exactly what I'm looking at, the minimum mass that can form stars, minimum halo mass. Alas, when I reran this, and I didn't do it at super duper high res because I didn't have time for that. We might do that later, but this of course is the first test. Even with Jose's late reionization, it has a minimal effect on the star formation history, and there's still no satellites. So that's just the first thing I tried. There'll be more things to try in the future. Okay, but then I just found out, since I've come here, that actually a few of the Fire 2 dwarfs are, oh, I'm out of time. That means I was talking fast. Okay, some of the Fire 2 dwarfs are forming satellites. So this is from Alex Fitt's work. These are just these standard high resolution, about 500 solar mass particles. Now, the trick is these, you can see they form satellites here. I guess I'll just go ahead and, this is from my Fire 1 work. So these are all Fire 1, but just to give a sense. This is MVIR, not M now. So in theory, they could move a little to the right. Oh, this is the mass of the subhalo that did not form stars in the simulation I ran, just for reference. Okay, so only 2 out of 13 of the Fire 2 M10s form satellites. Now that is, the problem with that is we didn't really run very many of the same initial conditions in Fire 1 and Fire 2. So it's really hard to say if there's actually something that has changed about Fire 2, or if it's all just at the mass range where we're so, it's such a critical mass range that a little change here and there and a little bit of stochasticity, even from running simulations, can have a big effect. So I do plan on looking at this further. Oh, I should also point out that Alex did run a super duper high res version of this, not quite as high res as the one I ran, but you know, almost, since we're having an arms race here. And if he also reproduced the satellite. So basically, I'll finish with my conclusions, but more or less what I hope to be able to do, although Phil told me not to jump down this rabbit hole, but is to kind of start turning things off and on one by one and see what we can do to make satellites appear or not. Okay, so in summary, this is a crucial mass scale for many reasons. I hope I've made that case to you. When you run at this high resolution, you can make much more interesting comparisons to observation. Resolution effects might artificially create blowouts or periods of no star formation. However, we're still forming cores in 10 to the 10 dark matter halos. We may have fewer satellites, more simulations necessary. In particular, I want to rerun this one, which was run in Fire 1. It had a very massive satellite of about 10 to the 5 and see what happens. And then because the existence of these satellites and also isolated ultrafaints can constrain reionization models and constrain physics, please observers go out and find one of these ultrafaints orbiting around a local group dwarf or an isolated dwarf so that we can start to figure out what's going on. Oh, and thank you both to the audience and to the UCI PR team, which is continuing its long-standing tradition of making mildly embarrassing PR photos. Thank you. Yeah, I think it was, I mean, that's the SIDM is fireproof, right? I mean, there are other ways, but if we're able to form cores with and without, I mean, we'll have to look at. Yeah, it's probably a better question for Victor, but.
But you're in a few billion solar masses and stars.
Yes. Thank you. There. Yeah, within the virial radius, which is about 50 kiloparsecs. I looked outside the virial radius, and we're just really not forming these objects even outside the virial radius. Actually, I put this back up here. This is not fit for publication. This is an old plot. I dredged up from my first paper, and it's got low and high res, and you can see we formed a lot of these 1, 2, 3 star particle objects that we, didn't decide ourselves to call galaxies, but even these objects are definitely not forming in Fire 2, whether that's physical or, so there is a big difference at the super duper low mass end.
Any other questions? If not, let's thank Coral again.